When people think about artificial intelligence, they imagine massive neural networks, billions of parameters, and incomprehensible math. But hidden underneath all of that complexity is one of the simplest tools in mathematics, a single number. This slide shows a neural network collapsing down to just one letter, C. And that's not a coincidence, because one number, used correctly, can control volume, confidence, speed, and intensity across an entire AI system. That tool is called the scalar, and once you see how it works, you'll start noticing it everywhere in AI. So, what does a scalar actually do? A scalar has a very specific job. It changes how strong something is without changing what it is. Think about audio. If you turn the volume knob down, the song doesn't change, it just gets quieter. Same rhythm, same melody, same structure. Or think about a direction arrow. You can make it longer or shorter, but it still points the same way. That's the core idea of a scalar. Adjust magnitude, preserve the content, and mathematically, that idea becomes incredibly powerful. When you multiply something by a scalar, only three things can happen. You can stretch it, make it bigger, you can squish it, make it smaller, or you can flip it, reverse its direction using a negative number. Nothing more, nothing less. The shape doesn't change, the information doesn't change, only the scale does. This simple behavior is exactly why scalars are so useful in AI systems. Let's get very precise. A scalar is just a number. No direction, no shape, no structure, just magnitude. On the left, you see the number 22. That's a scalar. On the right, you see an arrow. That's a vector because it has both magnitude and direction. Scalars don't point anywhere. They don't describe space. They only answer one question: how much? So what happens when a scalar meets a vector? It doesn't argue. It doesn't negotiate. It simply multiplies every component. If your vector has two numbers, both get scaled. If it has 1,000 numbers, all 1,000 get scaled. The direction stays intact, the proportions stay intact, only the size changes. This single rule powers enormous parts of machine learning. Here's a concrete example. Imagine this list of numbers represents an audio signal. Peaks, valleys, positive, negative, everything that makes up sound. Now we multiply the entire signal by 0.5. Every number is cut in half. The song doesn't change, the timing doesn't change, the meaning doesn't change. It's simply quieter. That's scalar multiplication in action. And this exact idea appears everywhere in AI. Let's do a quick visual calculation. Start with the vector for -3. Now multiply it by -2. Every component doubles in size and flips direction. The result is -8, 6. Same shape, same proportions, just scaled and reversed. This flipping behavior is especially important when AI models correct their own mistakes. This is the cleanest definition you'll ever need. If a number's job is to scale something else, that number is a scalar. It doesn't need to know what it's scaling, it just applies pressure, more or less. In AI, scalars control learning speed, confidence, attention strength, and output intensity, quietly, constantly. Now here's a question that reveals a lot. What happens if you scale a vector by 0? Every component becomes 0. The direction disappears, the magnitude disappears. You're left with the 0 vector. In AI terms, this is how signals get shut off. No influence, no contribution, no effect. This distinction matters more than most people realize. 50 miles per hour is just a number. That's a scalar. 50 miles per hour south includes direction. That's a vector. Scalars don't know where, they only know how much. And in AI, separating these two ideas keeps models stable, controllable, and predictable. So let's summarize. Scalars are single numbers. Their entire job is to scale things, and they do it by multiplying every entry. No exceptions. Simple rule, massive impact. This is why something so small ends up being so powerful. And now you're ready for the next step. Because once you understand scalars, you can start building with them. Combining scaled vectors, balancing influence, shaping behavior inside AI systems. This is where simple math turns into intelligent behavior. And that's exactly what we'll explore next.